I can already speak. I wrote the abstract to Enzo with the thin film related into it, but obviously that misled him. The talk will be more appropriate for tomorrow's session for the RF losses, but nevertheless, let's go ahead to hear it. No, this one. Surface topology. I'm sorry, which one is it? This is switch? Yeah, with this in the laptop. Yeah. Let's go directly to the outlines. First, we will show the 9-cell cavity yield, which is the motivation for those studies, which is we're doing quench studies. And now I'm going to show briefly, quickly, Argonne and the Fermilab joint facilities about cavity processing and our diagnostic abilities. As most importantly, among them are the surface replica. And I will briefly show the cavity processing testing summaries we have. And the most important, I think, interesting results I want to show you is cavity performance and the surface features we have try to correlate. And also for those cavities without the features but still quenched, we try to correlate them with the performance and the surface roughness. And then last of all, the Fermilab's effort to achieve the best surface roughness in Niobium cavities. And that's the starting point for the future thin film effort. Now, this is the typical, I think it's the latest, maybe it's not the latest, but quite fairly recently, the 9-cell IOC cavities reached a 56% yield. Those cavities without it's not achieving this goal. Majority of them are limited by cavity features. So we try to look at the cavity inside. Before that, I show a picture of the Argonne Fermilab facility, which is a state of the art. We're able to achieve very nice cavity results for the single cell. And once the cavity has been tested, we use the optical inspection to look at the inside with when the cavity is tested with the TMAP system, we look at the quench locations, and then we can go ahead and look at the inside. That was the two systems we use. The one is the Cudo system, and the one is the Questar system. That Questar system actually can reach 5-micron details. I did not update that. It's 10 micron. That's the old time. This is the picture showing the TMAP system we used. One of these, the second sound detectors around the outside of the cavity equator. And the other one is full body TMAP, and also the band thermometer on the equator. So we use the TMAP system to identify the cavity quench location, then use the optical inspection to find out where that is. After that, we try to use the surface replica to extract the surface topology for that locations. And that work is pioneered by Claire Antoine and his group. So we adopted the same thing at the Fermilab, which is now the system can actually capture the 1-micron details. Here's the verification of the detail of the replicated material. We use the man-made pit for this Niobium sample, and then we made a replica out of it. We compare these two. We can claim even better than 1 micron sometimes. Now, some people may question, this replica has limited resolutions. Are you sure the 1 micron details is sufficient to characterize surface in terms of magnetic field enhancement? And here's the work by Jens Noblock. He's here today. In terms of when the magnetic field achieves or exceeds the critical magnetic field region, HC, some of the areas becomes, at the sharp corner becomes normal. And if you calculate the normal conducting niobium's skin depths, that's about the micron range. So that tried to convince you that surface replica resolution for the 1 micron is pretty sufficient. Now, so I told you we use the TMAP to find out the location of the cavity quench, and then use the surface, and then use optical inspection to look at the inside feature. Then after that, we pour the silicon rubber into the cavity, pull them out. Once the silicon rubber is solidified, you already can see these features on the silicon. But the problem there with silicon is it's still a little bit of jelly. Like, you cannot put that onto the surface photometer. That's why you have to make a very hard epoxy positive version of this surface. Then you put it into the surface scanning using perfilometer. And of course, we have to worry about whether the silicon rubber will actually degrade the cavity surface cavity performance. We actually tested a couple of cavities. This is one example showing after the replica application, the cavity does not degrade. That means we can replicate the areas again and again and again without worrying about the problem. And here's the bragging slides that at Fermilab we highly optimized the single cell handling process. Within the past 12 months, we achieved the 22 cavity single cell processing without the single case of the field emission. That's strictly field emission because X-ray detector detects no above background X-ray signals. So that way we can actually confidently study the quench behavior of the single cell without the worry about the noise of the electron activities. Now, with all those things in place, we start to look at all the single cell we can get plus the 9 cell which has a problem. Those cavities includes 6 major categories. And for those cavities, if there's a geometric defect, there are either bumps, pits, or scratches. In some cases, with large grain cavities, there's a large, steep grain boundaries. And for those cavities without the visible defects, or that quench location simply is uniformly smooth, then we look at that region's the surface roughness in terms of the 3 areas. Now, next one, just to show you a couple of examples. Those are very representative for the different behavior of the quench. First one is the low quench field at the 12.3 megavolts per meter in one of the 9 cells we have looked at it. Actually, one of the features we found is by the TMAP and subsequently optical inspection, then we replicate the surface. We know exactly what that feature has the profile like this, very sharp corner and very deep. So I'm going to go through a couple of these similar features, then do some analysis to them. The second one is the famous AES1 cavity that has these twin bumps, which quench the cavity around 15 to 20 megavolts per meter later on after the repeated process. And this is, again, the rich information about this geometric contour of these 2 twin bumps. The next 2 cavities is basically a single cell. They both performed very well, almost to 40 megavolts per meter. Interestingly, that even though this cavity shows the quench actually happened at this location, this cavity, the quench actually happened not at this region. It's the different places. Now let's do a little bit theoretical calculation. We used we used 2 models. One is by Valery and Hassan. They proposed this pinhole model to calculate the surface, to calculate the field enhancement. And according to them, we calculated this that shows the calculated field enhancement factor versus measured. It's a little bit different, except that this one, AES4, which is a little bit closer, 1.08 versus 1.2, but the other 2 cavities are pretty far away. So there's something suggests that the model is overly simplified. Now, I want to go to the next cavity, which is the typical, also very famous large grain cavity, which is went to 43 megavolts per meter, made by Ningxia large grain triple R material. Peter supplied this cavity to us. Well, actually, Beijing University supplied this cavity to us, but Peter made a lot of measurement and the processing. Keep in mind that cavity quenched at the very high surface field. But again, we look at the cavity inside. What we found is very big, eye-catching steps right here. This is the weld seam, which means the magnetic field travels this way, and this is right cut across the magnetic field. And this is very deep. We looked at the sections from here to 60 micron deep, go over here to the 20 micron deep, and the edge is very, very sharp. And we use the Yang's simple model of the step to calculate the field enhancement. It looks like this area has field enhancement factor of 1.6. The field is, okay, it's 185. Somehow the other slide says 189, but it's okay. So what we actually learned from this case is that severe grain boundary doesn't seem to cause material imperfections in this cavity. And maybe the phonon peak actually helps to reduce the effect of this normal conducting region at this area. It's large. Because we know from Peter's processing notes that this cavity went through the heat treatment at 1250 C. That usually brings the phonon peak back. But again, you look at the field enhancement factor, that's something very interesting. Now here's the summary of the previous couple cavities with this large grain cavity altogether. We had computed the field enhancement factor based on the surface topology we get, and we have this measured maximum H field. You time this with this together. Here's the maximum H field based on the field enhancement factor you're supposed to get. So we'll look at the numbers you have. You have this case as 277 millitesla. You have this case as 296 millitesla. How is that possible? So there's something suggests to me the field, the vortex penetrates into the edge of these pinholes, something we don't understand very well. I'm hoping Ernie Brandt or Alex Grovich can help us to calculate how this field actually enhances in those regions. So our conclusion is that many cavity quenches, they found that the cavities, they cannot be explained by simple magnetic field enhancement. And surface topology seems to be it's a secondary role, because you know that area has high magnetic field based on the field enhancement model, but the cavity doesn't quench. And of course, that suggests that if you have a cavity actually quenched, then it must be because the intrinsic material imperfections, in our point of view. And again, in the large grain cavities, the severe grain boundary does seem to be a concern for some cases.